Hello students, welcome to another session of All Force e-learning program. Now in this session, we will derive the electric field due to a linear charged conductor, line of charge. The electric field due to a line of charge. We are deriving the electric field intensity, electric field strength due to a line of charge, due to a linear charged conductor. Linear charged conductor, linear charged wire, right? A charged, linear charged wire. Charged wire, we are going to derive the formula for the electric field intensity due to this, right? Yes, before going to this, let us recall the things what are necessary to derive this equation. So to derive this expression, what are the necessary aspects? Let us have a recall of all those things. So I was telling you, charge is the intrinsic property of the fundamental particles called electrons and protons. Wherever they exist, they exhibit that property. They show force, electric force, Coulomb force, they exhibit force. And every charge will have a field around it. The space around the charge where the effect of the charge can be experienced, felt, is called electric field, right? A charge exhibits lines of force. So the lines of force, whatever area to which these lines of force exist, to the appreciable value, right? Now that boundary, till that boundary, the space is considered to be electric field. Now every field has got strength. The characteristic property of the field, electric field strength or electric field intensity. By definition, electric field intensity E is the force experienced per unit positive test charge. E is force per unit charge. This is the definition of electric field intensity. Later we have derived the formula for electric field intensity due to a point charge. By applying Coulomb's law, we derived the electric field intensity due to point charge. We got the electric field intensity due to point charge as 1 by 4 pi epsilon naught q by r square, the magnitude of the field. If there are many point charges, multiple charges, we were applying the principle of superposition. The net resultant electric field strength due to all the charges is equal to the vector sum of all the individual electric field intensities produced by individual charges at that point, right? Considering all those things, the vector sum of that is the electric field intensity due to point charges. Later we have learned about electric flux. Flux, it is the measure of number of lines of force over a particular space. The count number is electric flux. By definition, electric flux density, it is nothing but the electric field intensity. It is electric flux per unit area. So cross multiplying flux is E dot A, it is dot product, or it is EA cos theta. For uniform field it is like this. For non-uniform field, the total electric flux is integral E dot T. For non-uniform field, generally for any field we can apply this. If it is uniform, you can directly take up the formula flux phi is EA cos theta. Later electric dipole, E, the combination of two equal and opposite charges separated by distance. We have derived the formula for the electric field due to dipole on the axial line, equatorial line and at an arbitrary point, right? Then the most important, we have considered Gauss law, right? We will be making use of Gauss law to derive this expression. So I was telling you, Gauss law, you know, Gauss law is an important tool to measure the electric field intensity due to uniform charge distributions. Now why Gauss law? Actually Coulomb's law is applicable, is restricted to find the force and field due to point charges, discrete point charges, isolated point charges. Even if there are many number of charges also, we apply principle of superposition to find the electric field intensity. But point charges, right? Later also for dipole, two point charges equal and opposite separated by distance, even for that also we used Coulomb's law to find. But if there is a continuous charge distribution, charge spread over a line, linear charge, continuously charge being distributed, then for such things we cannot apply Coulomb's law. Similarly, charged sheet, if charge is spread over a sheet like this, on a plane, if the charge is spread over a plane, then for such things we cannot use Coulomb's law to find the electric field intensity. In such cases, we use Gauss law to derive the equation. So Gauss law, an important tool, it has got three uses. First thing, it is used to find the electric field intensity due to symmetrical charge distribution, uniform charge distribution, like charge due to linear charged conductor, charge on a plane sheet, charged plane sheet, infinite plane sheet, spherical shell, charged spherical shell, conducting, non-conducting, or non-conducting charged sphere, so on, cylindrical conductor, so on and so forth. For all such, we can find out the electric field using Gauss law, right? So first thing, you can find the electric field intensity. Second, you can find the flux over an enclosed volume. The flux emerging from an enclosed space, enclosed surface, the total flux, we can measure the flux from a surface. Or we can even find out the charge that is enclosed inside the closed surface. What charge is, how the charge is being distributed inside the enclosed surface. Even that can also be measured. If you know the charge inside, we can find the electric field. If you know the electric field, we can find out the charge that is distributed inside. So this way, it has got vital uses there, right? Very important this thing. So using that principle, let us find out the electric field intensity due to a charged wire. Now let us consider a linear charged conductor, like this. Infinite long charged conductor. Actually the charge is infinite long. It is extending to this side, it is even extending to this side, right? A linear charged conductor. It is uniformly charged over the surface like this. It's uniformly charged over it. Linear charge conductor, uniformly charged, right? I was telling you in the previous video, when I consider linear charged conductor, how do you calculate the charge? How the charge is distributed over the objects, right? If it is for linear conductor, we were defining linear charge density. If the charge is spread on a plane, I defined a surface charge density. If the charge is now inside a volume, inside a body, throughout the volume, if it is spread, we defined volume charge density. Similarly, for this linear charge conductor, it is having a linear charge density lambda. It is having a linear charge density lambda. Now, according to the definition of linear charge density, I said lambda is equal to Q by L, charge per unit length. So the charge that is associated to a particular length L of the conductor is lambda into L. So according to the definition of linear charge density lambda, it is charge per unit length, Q by L per unit length, right? If it is uniformly distributed, you can directly take like this. Had it been non-uniform distribution, then lambda you can define it as dq by dx or dl. For a small particular length, for a small element of length, let the charge be dq. At that element, let the linear charge density be lambda. So lambda is dq by dl. You can find out dq is equal to lambda dl. In general, you can use this for any linear charge distribution. But if the charge distribution is uniform, if the charge is uniformly distributed, right, equal charge per unit length, every centimeter same charge, first centimeter some q charge, another centimeter same charge, same amount of charge. If it is uniformly distributed, then you can directly write down lambda is q by L, or q is equal to lambda L. So please remember this, because this we are going to use in this derivation, right? So linear charge density. So before going to the derivation, we should know the basic things that are required to derive the equation. So these are the basic things. I am just recalling all the things what are required there. So consider a linear charge conductor where the charge is uniformly charge distributed. Its linear charge density is lambda. So lambda is q by L, charge q is lambda, right? Now how do you find the electric field? I was telling you in the previous video, to find the electric field you have to follow certain steps. There are certain steps you have to follow, based on which, according to the steps, you can derive the electric field due to any charge distribution. Well, it will be easy if it is charge is uniformly distributed, right? So first step, whenever you are asked to find the electric field intensity due to any charge distribution at a point P, now consider the point P where you are asked to find the electric field intensity. Let the point P be P. Here the point is P at a distance small r from this linear charge conductor, right? So we are asked to find the electric field intensity at point P at a perpendicular distance r from the linear charge conductor. Now, to find the electric field, the first step, imagine a Gaussian surface. A Gaussian surface, I was telling you in the previous video, a Gaussian surface is a imaginary enclosed surface which encloses the charge inside, which is symmetrical to the shape of the charge that is considered. You have to consider a Gaussian surface symmetrical to the charge that is being given. Like for example, if the charge is a linear charge conductor, a wire, thin cylindrical wire, then we have to imagine the Gaussian surface of cylindrical shape, right, uniformly distributed, cylindrical shape, right, equidistant from that conductor. Suppose if it is a point charge, imagine a spherical Gaussian surface. If it is a spherical shell, imagine a spherical Gaussian surface. If it is a plane sheet, then imagine a plane surface, right, a cuboid like plane surface parallel to the plane sheet. So this way, according to the charge that is being given, according to that you have to imagine the Gaussian surface. The Gaussian surface should be symmetrical to the charge that is being distributed inside. So our charge now is a thin wire. A thin wire is like a thin cylinder whose radius is very much small when compared to its length. So it is cylindrical, thin cylinder. So we shall imagine a Gaussian surface which is also a cylinder, right? A cylindrical Gaussian surface around this linear charge conductor that is given, around the linear charge conductor that is given to us to find the electric field, and which is symmetrically placed with respect to this conductor, right? Now you should consider the Gaussian surface such that the given charge lies exactly along the axis. If it is a cylinder, it is along the axis of the cylinder. The Gaussian surface is such that the axis of the Gaussian surface should coincide with the charge that is given. The charge must lie along the axis of the Gaussian surface, right? Suppose if it is a point charge, then the spherical Gaussian surface should be such that the center of the Gaussian surface will be the point where the charge should exist. Charge must be at the center of the Gaussian surface. Suppose if it is a sphere, then concentric spherical Gaussian surface should be imagined. So the Gaussian surface imagined should be symmetrical to the charge that is being given, whatever charge that is given to you to find the electric field. First point. Gaussian surface is an imaginary surface. I was telling you, it need not be a physical body, or it need not be a surface of a body, physical this thing. It is a hypothetical surface. We are imagining the surface, but you should be very careful while imagining the Gaussian surface that the Gaussian surface, shape of the Gaussian surface should be symmetrical to the charge for whom you are finding the electric field, and it should be placed symmetrical to that charge also. Like here in this case we are given with linear charge conductor. Now imagine a cylindrical Gaussian surface such that the axis of the Gaussian surface coincide with the linear charge conductor, right? So that all the points on the Gaussian surface will be equidistant from the cylindrical conductor like this, right? First point. Second, you know, I was telling you, you should imagine a Gaussian surface such that the surface should pass through the point where the electric field intensity is to be found. Where you have to find the electric field intensity, that point should lie on the Gaussian surface. So you should imagine a Gaussian surface such that it passes through the point where we have to find the electric field. Second point. Right? So I considered a point P, Gaussian surface which is exactly passing through the point P like this. Second, like this. Now later, so it is an imaginary surface, there need not be a physical body, it should be symmetrical to the charge that is being given, and it should be symmetrically placed with respect to the charge distribution, and it should pass through the point where the electric field is to be determined. Next, the direction of the electric lines of force. Gaussian surface should be imagined such that the direction of the electric field intensity is either normal to the Gaussian surface or tangential to the Gaussian surface. It should be imagined such that it is either normal or tangential. Now you see, if I consider this linear charge conductor, the lines of force for this charge conductor will be normally spreading away like this. Normally spreading away from the conductor this way. Now if I show it in this manner, let me put the diagram in the other way, right? Suppose, let me take this conductor in this manner. This is the conductor, suppose. If I consider this as the linear charge conductor, then the electric lines of force from this will emerge normally out like this. Normally outward normal to the charged conductor like this side, and even to this side also. Throughout the circumference, they emerge normally outward. And our Gaussian surface, this is the Gaussian surface we imagined. This is the Gaussian surface which we imagined. Now the lines of force emerge outward normal to the Gaussian surface. They are emerging outward normal to the Gaussian surface. Like this. Here also they are emerging outward normally. So here it is this way, here it is this way. At any point the lines of force they are emerging outward normal this way. If I see from this side, suppose this diagram, let us visualize this diagram from this side. From this side, if I see this picture, this is the conductor. Like this is the linear charge conductor. Now I am putting the diagram this way. This is the linear charge conductor. Charge is distributed in this manner, right? Around this, the Gaussian surface is in this manner. So I am drawing this diagram. This is the linear conductor. This is the point. So I am picturizing in this manner. This is the linear charge conductor, and this is the Gaussian surface, the circumference of Gaussian surface. So this is the charge. You know, from the charge, the lines of force emerge normally outward like this, right? They are emerging normally outward in this manner. In this manner. You see, on the Gaussian surface, the lines of force are normally emerging out. So this is one of the conditions where, when you imagine the Gaussian surface, this is one of the conditions that the surface should be such that the lines of direction of the electric field should be either normal or tangential. And even here, if you see at this point on the circumference, the top here, on the top circular part of the Gaussian surface, the lines of force are like this. The lines of force are here tangential to the circular part of they are tangential to the circular part. Here also at this point, they are tangential to the circular part of the Gaussian surface, what we have imagined like this. And here they emerge normally out. So here the lines of force are normally outward like this. So if I take, this is the linear charge conductor, our cylindrical surface is this way. I picturize this in this manner. Now if this is the linear charge conductor, our Gaussian surface, the lines of force from the charge conductor will emerge this way. At any point they are emerging normally out. And if the same picture is visualized in this manner, right, this is the charge concentrated here, this is the line of charge, and this is the circular part. The lines of force are emerging like this. At every point they are emerging normally out of the Gaussian surface. They are emerging normally out from the curved surface, and they are tangential to the circular part of that the Gaussian surface. The condition for the electric field is direction of the electric field is satisfied, right? So this way you should consider. You should be very careful. Now this is the important part of the derivation. Later the mathematical approach is easy. The mathematical approach is easy enough to derive the thing. But it is very important to imagine the electric field in the Gaussian surface around the charge. The later mathematical part is very easy. If you are done with this, then it is very easy. Okay. Now, cleverly considering the shape of the Gaussian surface, to the given charge distribution, right, like this. Then now imagining the direction of the electric field, we have understood the direction of the electric field is outward normal here. At the point P, the direction of the electric field is outward normal. Throughout the circumference, if I imagine, the direction will be outward normal like this way it is, right? This is the most vital part of the derivation. Okay, so let the electric field at this point be, and the direction is outward normal. Good. Then at this point P, imagine a small area element ds, right? An area element ds at point P. I was telling you, whenever you consider a surface, for any surface, the direction of the area element is outward normal, away from the surface, normal to it. So to this area element, the direction is outward normal. So therefore ds. So therefore, if I consider E dot ds, the small flux through this area element, the small flux emerging from the area element d phi, we know according to the definition, small flux is E dot ds. E dot ds, right? And so this is a Gaussian surface of radius r, and let the length of the Gaussian surface be L. The length of the Gaussian surface is L. If the length of the Gaussian surface is capital L, then the charge, the amount of charge that is enclosed inside this Gaussian surface from here to here, the amount of charge, according to the definition of charge density, we know lambda is Q by L. So the charge that is enclosed inside the Gaussian surface, Q inside, is lambda into length of the conductor that is inside the Gaussian surface. So let the length of the Gaussian surface be L. So it is capital L. So charge inside this is lambda into L, equation 1. Right? Now, considering the small element ds here, the small flux through this element d phi, it is E dot ds, right? E dot ds. Then, if I imagine such area elements throughout the surface of the Gaussian surface, all the elements, then the total flux from the Gaussian surface emerging from this Gaussian surface, total flux phi, it is integral d phi. So the total flux is equal to integral of d phi, that is E dot ds. But you know, E and ds both are in parallel direction, so they are parallel. Integral, it is E ds cos of, since both are in same direction, cos 0. Cos 0 is 1. So the total flux is equal to integral E ds. Right? This is another equation, intermediate equation. Now, coming to the field E, we have imagined this Gaussian surface symmetrical to the charge. All the points on the Gaussian surface are equidistant. So therefore flux, total flux is E integral ds. E integral ds. Now total surface area of this cylinder, it is E of, the total surface area of this cylinder is, it's 2 pi r into L. 2 pi r into L. This is equation 2. Now, we have taken the flux, total flux due to the curved surface. Now you get a doubt, sir, how about the flux through this circular part on the Gaussian surface? You know, here the field is parallel to the Gaussian surface and the normal to this area is this way. Angle is 90. The flux through this circular part is 0 because the angle is 90. It is EA cos 90. Even here also the direction of the electric field is like this and the area element is perpendicular. The flux due to the circular part is EA cos 90. It is 0. So the total flux through this Gaussian surface, flux through the curved part plus flux through the circular part, but flux to the curved circular parts is 0 because the field is parallel to circular part, area vector is normal, angle 90, flux 0. Even here through the circular part, here is 0. So on the upper circular part and the lower circular part, in these two parts the flux is 0. The only thing is curved part, and that flux to the curved part is E into 2 pi RL. Okay. Next, according to Gauss Law, so the statement for Gauss Law says that if a charge is enclosed in a Gaussian surface, it is enclosed in a surface, the total flux through the Gaussian surface is directly proportional to the charge enclosed inside, or the total flux is 1 by epsilon naught times the charge enclosed inside. So therefore flux enclosed inside is equal to total flux is Q inside by epsilon naught. This is equation 2. Now substituting equation 1 and equation 2 in equation 3, we get total flux. It is E into 2 pi RL is the charge inside is equal to lambda L by epsilon. So therefore L gets cancelled, right? I take this 2 pi R this side. So I get the electric field intensity is equal to lambda by 2 pi epsilon naught R. This is the electric field strength due to the magnitude of the electric field strength due to a linear charged conductor, line of charge distributed in a line, uniformly distributed in a line, charged wire, a uniformly charged conductor, a thin glass rod charged uniformly. For all such things, the electric field, magnitude of the electric field due to that charge conductor E is lambda by 2 pi epsilon naught R. Or you can even write it in general form, 2 lambda, multiplying 2 dividing by 2, it's 1 by 4 pi epsilon naught R. Well, 1 by 4 pi epsilon naught is a constant, Coulomb's constant. So that constant into 2 lambda by R it is. Because usually we find in all equations 1 by 4 pi epsilon naught is a constant. We have even deduced the value for 1 by 4 epsilon naught. It's 9 into 10 power 9. While doing the problems, better take it as 2 lambda by 4 pi epsilon naught R, because 1 by 4 pi epsilon naught R epsilon naught will be 9 into 10 power 9. So simply 9 into 10 power 9 2 lambda by R. So that is the magnitude of the electric field intensity due to a linear charge conductor or thin line of charge, uniformly distributed charged wire, for which the electric field is like this, E is equal to lambda by 2 pi epsilon naught R. Then if we write in vector form, now what is the direction? Direction of the electric field is along the radius vector R. So if we write this in vector form, I get electric field E bar is equal to, this is lambda by 2 pi epsilon naught R, it is R cap. Or E bar is equal to lambda by 2 pi epsilon naught R cap is R bar by mod R into R, it is R square. So the electric field vector finally, it's lambda by 2 pi epsilon naught R square R bar. This is the vector form of the electric field intensity. Magnitude is lambda by 2 pi epsilon naught R and the direction is outward normal away. For positive charge, if it is positive, the direction is outward normal away. So the lines of force will be away. Flux is positive flux. Lines of force emerge out of the surface. So therefore it will be positive, outward flux. But if the charge is negative, right, then the direction is towards the charge. Inward flux, the direction of the electric field will be towards the conductor there. So therefore E is purely in the direction of the radius vector. For positive charge it is parallel to it, for negative charge it is opposite to it. So this is the formula for the electric field intensity due to a linear charged conducting wire. Okay, thank you.